All right, we'll get started here. First, thank you guys very much for coming. I know it's the last session. It's been a long week here at reInvent. I'm going to take you guys through best practices with Amazon Redshift. My name's Tony Gibbs. I'm a data warehousing solution architect here with Amazon Web Services. I always like to kind of just get a feel for where you guys are at. How many of you people in the room here aren't using Redshift today? Maybe you're just here, you're evaluating it, that sort of thing. Okay, so quite a few of you. How many of you use Redshift today, day in and day out? Okay, so much less. I actually thought that might happen today. Just to level set, this presentation is primarily meant for existing Redshift users. It is a technical 400 level deep dive. That being said, I'll slow down a little bit in the architectures and concepts and try and fill in a little bit more for the rest of you that haven't used Redshift yet. This section really will be review for the experienced Redshift users. Then I'm going to jump into data ingestion, basically how you get data into Redshift according to our best practices, how to do ELT in Redshift. Then I'm going to go into workload management, which is one of our more advanced concepts. So cover that. Hopefully, you'll walk out of here with enough information where if you are going to be going back and configuring Redshift, you'll be able to set up a basic WLM configuration. Then I'm going to do cluster sizing and resizing. This is really kind of information that will be for everyone. It's actually one of the most frequently asked questions that I get in how do I size a Redshift cluster. I'm going to wrap up by giving you guys some additional links, resources, kind of blogs and that sort of thing that we find useful or that we find that customers find useful. And I'll give you that to go. If there is time left over, I'm happy to do open Q&A. I'm not sure if there's microphones out or not, but if there are, I'll do open Q&A. I will also answer questions out in the hallway lobby area out there as well. So if you guys have a lot of questions and we're getting kicked out of the room, we can go stand out there and I'll answer questions for as long as you guys have them. So let's get started here. Redshift really kind of starts out from being a fork off of Postgres. Basically, we forked it off of Postgres. We rewrote the entire storage engine to be Columnar. So it's Postgres SQL, Columnar, data storage. We also made it MPP, which is massively parallel processing. This allows us to scale Redshift out up to 128 nodes or 2 petabytes of raw storage. We added a lot of analytics functions, windowing functions, and that sort of thing, approximate functions, basically the types of stuff that functions you want to have in an analytics database. We wrapped it all up in the AWS ecosystem, so this is tight integration with S3, where you typically load and unload data from. Integration with things like KMS, so you can do full disk encryption. IAM for authentication, so you can authenticate to Redshift using IAM. The combination of all of this really is what makes Redshift what it is. We launched Redshift on Valentine's Day 2013, so almost 6 years ago. Since that time, we've continued to innovate and add more features to the service. We roll out patches typically on a 2-week cadence, so every 2 weeks, typically get a new patch. This is entirely automated. You set a 30-minute maintenance window, 30 minutes when you want that patch, and we will take care of all of the patching, both to Redshift, the operating system, and any type of security updates that need to happen. All of it kind of happens automatically because Redshift is a fully managed service. Looking at the Redshift architecture here, I'm going to start out with this top green box here, which is SQL Client Tools. That's what you connect from. So we supply both JDBC and ODBC drivers. Because Redshift was forked off of Postgres, we've maintained that compatibility so that you can actually also use the open source Postgres drivers. So say, for example, you were connecting from Python or R or Ruby or some other language like that, you can just use the open source Postgres drivers and you can use those to connect to Redshift. Your connection goes to what we call the leader node. That's that blue box there up at the top. The leader node acts as the query coordinator. Also holds all of the metadata about the table. So if you're familiar with Postgres, the PG catalog, that resides on the leader node. Behind the leader node, we have between 2 and 128 compute nodes. In this example, I just have 3. That's where all of the data resides. So All the data, hopefully, is spread evenly across the cluster. I'll talk about how you spread data out across the cluster later. When you execute a query on Redshift, every one of those compute nodes executes it entirely in parallel, which is a really important concept. It's kind of why we call this massively parallel share-nothing architecture. Underneath the compute nodes is S3. That's typically how we ingest data. We either load it, or if you want to remove data out of your Redshift cluster, you can unload it. The backups in Redshift are entirely taken care of for you. Redshift just backs up data asynchronously in the background, and that also synchronizes to S3. If you were to restore a cluster, that also comes off of S3. All of those operations should happen in parallel. A little over a year and a half ago, we launched what we call Amazon Redshift Spectrum, which was really an extension to Redshift. It's this elastic layer of compute that sits between your compute nodes and S3 and allows you to query S3. So if you say, for example, have a data lake and you have all these Parquet files sitting on S3, you can expose those Parquet files in your Redshift cluster as an external table and query them. That query gets pushed down in this compute layer. That compute layer pulls the data up off of S3, returns results up to Redshift. You can even join tables that reside on S3 with local Redshift tables, and Redshift knows how to push or pull data in whichever direction it needs to limit the amount of data movement. So the first piece of terminology I'm going to introduce you to is Columnar. Redshift is a Columnar data warehouse. What this means is that we store data on disk column by column rather than row by row like a traditional database like Postgres. The reason we do this is that the types of queries that you typically execute in an analytics database really usually only query a subset of the columns. So we're able to reduce the amount of I/O that's needed to be done. Just to illustrate this, say if I have this deep dive table up here, you can see the DDL for it, and I have just a handful of rows there. And I want to execute this select statement. It's just a very simple query. I'm just selecting the minimum data out of this table. In a row-based database, assuming there's no index or anything like that to help you, you would end up having to read all of the data in this entire table to find that minimum date. In Redshift, because it's a columnar data warehouse, all we need to do is look at the data in that date column to find the minimum date. We don't need to touch the other columns. And that's the advantage of a columnar data warehouse for these types of queries. So the next piece of terminology is compression. Sometimes we'll use this term interchangeably, compression and encoding. So if you hear me say encoding, compression, I'm really kind of talking about the same thing. This really does two things for you. The first is compression allows you to store significantly more data in your Redshift cluster. Typically, we see somewhere between 3 and 4 times compression. These days, with the new compression types that we've added to Redshift, it's closer to 4 times compression, but I still kind of always assume 3 times is a safe number that you'll get. The second thing is compression also improves performance. So the reason why is it reduces the amount of I/O that we need to do off disk, and therefore still it actually does help with performance. The first time you load data into a Redshift table with the copy command, we will automatically apply compression to that table. So if you haven't set compression on an existing table or a new table, the first time there's a load into it, we will automatically set it. We also have this command called the Analyze Compression command. The Analyze Compression command, you can just type out Analyze Compression, the name of a table, and if there's data in the table, we sample the data out of that table and we figure out the optimal compression for that table. Just as a simple example, same table, same rows. We have 12 different encoding types. Basically, we can apply those encoding types by modifying the DDL. This is the manual way to do it. So you can see the encode ZSTD, which is Z standard, byte dict run length, for example. And one important thing to note is that each of these columns can grow or shrink independently. So some columns might be longer than others, and that's because some data may compress better than others as well. Because all of the data types in each of these columns are all stored together, each of these would be maybe all timestamps, or in this case, all integers, for example, or all chars. they compress very well. So that's one of the other advantages of Columnar and compression together. Our best practices are to apply compression pretty much to every table. One thing you might notice, though, is our analyzed compression may at times return back an encoding type called raw, which basically means there's no compression at all. The reason it does this is if you have a really small table, like maybe, I don't know, 10,000 rows, for example, there might not be any benefit to applying compression, so Redshift will say, well, it's better just to leave this uncompressed. Same thing if you have sparse columns. If you have columns filled with a lot of nulls, because of the way Redshift does nulls, you might also get raw back on those columns as well. I have a little snippet of SQL here. That's just where you can find the encoding type on an existing table. So the next piece to introduce you to is blocks. Blocks really are just, they're blocks. They're what we store our data in. The important thing to know here is that they're immutable and very large, 1 meg. We use 1 meg immutable blocks that will be encoded with one of 12 encoding types. Because when you apply compression, and because they're so large, they can actually, in certain cases, store millions of values. So you think about that, that's millions of rows stuffed into a single block. So they are very big. The next piece to introduce you to is something we call zone maps. Zone maps they're basically an in-memory data structure that stores the minimum and maximum values for every single block that we have on disk. That way, when a SQL query executes, say with a predicate, we can check that in-memory data structure and know if we need to read that block off disk or not. The next piece of terminology introduced to you is data sorting. This is really just the physical sorting of data on disk. So for example, you can say, like, I want to sort by this column, and the data will be physically stored on disk, sorted by those two columns. The reason or the primary purpose of sorting, or why you want to use it, is to make the zone maps more effective. So just as an example, same table, same data as before. I'm going to apply a sort key to this. So you can see the modified DDL up there. I'm first going to sort by the date and then by the location. In this example, the table is going to be first sorted by this date, and then when there's a tie, we're then going to look at the location and then sort by the location. So that's basically how data sorting works in Amazon Redshift. So tying the two concepts of zone maps and sort keys together, because like I said, sort keys, their primary purpose is to make the zone maps more effective. Say we have this table with these 4 blocks. You can see the zone maps kind of written out there. And we came along with a SQL query, and we're just going to count the records on a particular date. Redshift is going to first check the zone maps and look to see if it's possible for data to be in each block. In this example, we know that there could be data in those 3 blocks, and in this case, we've reduced I/O. If, however, we came along and we sorted this table by this date column, we would end up with zone maps that are going to be perfectly in sequential order like that, and now we've reduced I/O further. So the primary purpose of sort keys is to make these zone maps more effective. They typically go on the columns that you're using to filter on, basically your predicate columns. A few best practices around them. One is you'll usually want to apply it to the columns that you typically filter on. In a data warehouse, that's usually a timestamp or a date column or something like that, because we're almost always querying data between various dates. So that is one of the primary columns that you will want to sort by. If you do have a column or you want to sort by multiple columns, it doesn't make sense to sort on an extra column if you have something that's really high cardinality. So imagine you had a timestamp that went all the way down to seconds, and you had all of these values all the way down to seconds. It wouldn't make sense to apply a second column after that. So just kind of a little bit of a catch there. One thing is we also have a couple of scripts up here on GitHub. Those scripts that we have up there, if you have an established workload that runs on Redshift, they can help you determine if you have the correct sort keys or what should be the correct sort keys or not. One thing, also small note, if you have really small tables, it usually doesn't make sense to sort them. If there's like 10,000 rows, it's all going to be in a single block anyways, so that you're not helping out with the zone maps. This next piece is materializing columns. Again, this is also to make Redshift able to leverage the zone maps better. Sometimes I'll see, I'll just step back. There's two things on this slide. One is with dimension tables, and the other is with functions and such. So I'm going to talk about the dimension tables first, because this is actually one of the most common ones. A lot of data warehouses have these time dimension tables. Basically, they're unchanging dimension tables for the most part, and you're typically filtering on them. Well, what's going to happen if you look at this first example of these two lines of SQL here is we're going to end up running this predicate on this dimension table, which has a very small number of rows, and then we're going to join it back to our fact table. And that's going to result in essentially a full column scan on that fact table with a hash join. This second example, where I've materialized and taken the values from that dimension table and written them out into my fact table, that will allow Redshift to use the zone maps and reduce I/O on the fact table. This will run significantly faster if you do that. The second is around calculated columns. So if you are doing calculations on columns, typically in the where clause, like as I have in this example where I'm extracting an epoch out of a timestamp, that won't be able to use the zone maps. In fact, what's going to happen is you're going to go through every value in that column, extracting that value, just so you can do the comparison. If instead you actually materialized or rewrote out that value, what would happen is we could use the zone maps and dramatically reduce I/O. So just a couple best practices there on materializing out or writing out extra columns. Because Redshift is Columnar, writing out a few extra columns to a table or having very wide tables, there's not a lot of penalty to that. You pay a little bit extra for storage, but it has a dramatic impact on performance. Slices are a really important concept in Redshift. They are basically like, you can almost think of them like virtual compute nodes. They're essentially how we get parallelism within each one of our compute nodes. So as our 8XL nodes, for example, which I'll talk about later, they're split up into 16 slices. So it's almost like there's 16 virtual compute nodes inside each slice. We also store data per slice, and every slice only works on the data that belongs to it, which kind of leads to how do we distribute data in Redshift? There's 4 ways of doing this now. The first is distributing by what we call key. This is essentially where you pick one of the columns in your table to be the distribution key. And what we do is for each one of the rows, we take the value for that column, we hash it. That hash corresponds to one of the slices, and that's where the entire row resides. The next is what we call distribution style even. Even is where you just say, Redshift, please round robin this data for me. And Redshift just evenly spreads the data across the cluster. Then we have distribution style all, which is kind of a special case one, where we make a complete copy of the table on each node in the cluster. This is kind of meant more for small dimension tables. That's the primary purpose for dist style all. We just released distribution style auto. You might not have it yet. It's working its way through the various regions as we roll out patches. It's out in some regions, but not in all yet. And distribution style auto is the new default in Redshift. So all new tables going forward are going to be created with this if you don't specify something. What it does is it combines even and all together so that a table, small tables, start out as a dist style all, and when they reach a certain size, they switch to distribution style even automatically and are rewritten. So I'm just going to illustrate these. Let's say we have 2 compute nodes here. These are our little nodes, and they each have 2 slices. And I have the same table I've been working with all since the beginning, or since we started. And I have these 4 rows which I'm going to insert into here. The current distribution style, which you can see dist style even there up on the table, is even. I'm going to distribute these 4 rows in here. With even, the data simply round robins through the cluster, just like that. And Redshift evenly spreads the data. If we went with and picked a distribution key, so in this example, I'm going to pick the location column. So you can see dist key, dist key, location there, or dist style. And the values for it are SFO, JFK, SFO, JFK. So SFO might hash here. JFK, we'll say hashes there. SFO is going to go back to that slice 0, and then JFK over here. This is an example of a bad distribution key. being picked in Redshift. The reason why is if you executed a SQL query against this cluster, you can see that the second compute node doesn't have any data on it, and it does none of the work. So this is what we don't want to have happen. So what I'm going to do is I'm going to pick a better distribution key. So I'm going to pick this AID. You can see it looks kind of like a primary key maybe. It's 1, 2, 3, 4, high cardinality. And in this case, maybe 1 goes there, 2 there, 3 back over there, and 4 there. I made the example work perfect. So that is an example of a good distribution key. If you have a significant amount of data, millions of rows, for example, and you have a nice key like this, it will statistically give you a nice even spread of data. Then what we have is distribution style all. Like I said, this is kind of a special case for small tables, dimension tables and such. What we do here is we write to the first slice on every node. So in this case, all 4 rows are represented on both nodes in the cluster. So just to summarize where you use each of these, distribution style by key is typically used to co-locate data in Redshift. This is usually meant for large joins. So if you have, say, 2 large fact tables or a fact table and a really large dimension table, if you're able to distribute them by the column that's in the on clause in your SQL statement or on your join, that will result in both rows being on the same slice, and the join will be significantly faster. There is one catch. You want to make sure that you don't cause that skew that I showed in that one example when I picked the location. To see if there's skew, I have this SQL query up here. It's one of the system tables. It's svv_table_info. And in there, there's a column called skew rows. This skew rows has a ratio, a value in it, that has the ratios between the slice with the least amount of data and the slice with the most amount of data. Ideally, that value should be close to 1. So in this case, I have 1.07. That's a great skew. I'd say, rule of thumb, anything under 1.3 is totally fine. The other reason to use dist_style key is if you're moving data from one table to another with an insert into, with a select statement, that if both tables have the same distribution key, that operation will also be significantly faster. Dist_style all, our rule of thumb here is that the tables should be under 3 million rows. It also causes a type of co-location, so the joins are also really fast with these smaller dimension tables. And they also, actually, they store small tables actually more optimally as well. I used to always say, if you don't know or if you're not sure, stick with dist_style even. I think going forward, I'm going to have to say, if you're not sure what to do here, stick with dist_style auto. Dist_style auto, like I said, is brand new. It's not in all regions. You guys should have it hopefully within the next few weeks. It should be everywhere. But yeah, dist_style auto, like I said, combines all and even together. So just to summarize the best practices on table design here, we want to add compression in pretty much all of our tables as long as we can. We want to make sure we have sort keys on the columns that we primarily filter on. So this is, like I said, usually timestamps. We want to materialize those columns into our fact table that we're running those predicates on. We want to pre-calculate certain columns where it makes sense. Co-locate columns for our joins. I didn't really mention this, but the temporal columns usually make a poor choice of distribution. So I think based on time, usually doesn't distribute very well. Worst one I've seen, I think, is when someone picks like month to be the distribution key. It does not work. Lastly, if you have data types, keep them as narrow as they kind of need to be or as big as they need to be. I sometimes see like these migrations from Oracle and everything is a varchar 255. I'm not sure why, but that's just what people from Oracle pick. So make them shorter. It doesn't change storage footprint in any way, but it can impact query performance. It uses a little bit more memory in Redshift. So if you can, keep those as narrow as they need to be. So let's get into data ingestion. So one of the things, Redshift, the nodes are significantly bigger than we advertise. I don't think this is anywhere in our documentation or anything. So I think, like, for example, if you look at our 2 terabyte instance type, it actually has 6 terabytes. The reason it has so much space is that we mirror all the data on every node to another node. So your data is safely written to 2 nodes the moment a commit happens in Redshift. We obviously also have space set aside for temporary the operating system, all of that stuff. So the space that we advertise is the usable amount of space that you as a customer have for your data. That being said, like I said, the commits there, when a commit occurs, data is on both tables, or 2 nodes, sorry. The other thing is we also are asynchronously backing up all of our data to S3 in Redshift as well. So that kind of happens in the background. Our temporary tables, though, they're kind of special. They're not backed up to S3, and we also don't write out that mirrored copy. So because of that, they actually write twice as fast. Redshift is fully ACID compliant, fully transactional. It uses isolation level serializable. There's a 2-phase commit. There's a local commit that happens on each node, and then a global commit that happens across all of the nodes every time a commit happens. We've dramatically improved commit performance. It was about last July, August. We put out some patches that had a large impact on that. Even still, it makes sense to try and group workflows together into a transaction to reduce the number of commits that happen. One thing that customers will sometimes do is they'll have a bunch of DDL, and what they don't realize is that each one of those DDL statements is implicitly creating and committing a transaction. DDL is transactionable in Redshift. So I'm going to talk a little bit about the copy statement. The copy statement is how we typically get data into Redshift. In this example, I have this DC2 8XL node type. It has 16 slices. And I'm going to use the copy statement to ingest this one large file. What would happen is the leader node's going to check S3. It's going to notice that there's this file on S3, and it's going to have, in this particular case, the first slice in the cluster, load that file up. It's going to parse it, distribute it, write it out to disk across all the slices. This isn't exactly very efficient. If I took this exact same file and I split it into 16 chunks, for example, because this cluster has 16 slices, what's going to happen is every one of those slices is going to be able to reach out to S3 and ingest that file in parallel. So our rule of thumb is to have as many files as you have slices or a multiple of that. So if, for example, you had 32 files, that would work just as well. Ideally, these files should be somewhere between 1 meg and 1 gig after gzip compression. Just some best practices. These are kind of from what I've seen with customers. I always suggest just picking, using delimited files, picking a simple delimiter like pipe or comma, tab, whatever your preference is. Don't pick something crazy like a UTF-8 unprintable character. Pick a simple null character. Make sure things are wrapped in double quotes for your varchars. Use an escape character for double quotes and things like that. And then to get the number of slices in the cluster, that's a SQL query that you can use to get that. So I know I kind of mentioned you want to have as many files as you have slices. That's where you can find that. One pattern that customers have started using Spectrum for, so like I said, we released Spectrum, which is essentially external tables, is to ingest data through it. And there's a couple advantages for using Spectrum for this. One, you have full SQL. So you can aggregate incoming data with Spectrum. You can select a subset of columns with Spectrum, or you could also filter out rows that you don't want with Spectrum. So you can do a lot of data cleansing on the incoming data out of S3. And that's not something you can do with a copy statement. So one of our kind of, if you would like to, or if you think that it would be beneficial to you, definitely check out using Spectrum to ingest your data if there's some benefit for you. Redshift is really designed around big data. It's not meant for small ingestion. Because the blocks are so large in Redshift, being 1 meg blocks, the amount of overhead to ingest just a handful of rows is roughly the same as ingesting hundreds of thousands of rows. So ideally, you want to be ingesting fairly large batches of data. Word about update and deletes. Deletes simply mark rows for deletion. They don't actually remove the rows. Updates mark a row for deletion and reinsert it to the end of the table. So this is also one of the frequently asked questions that I get is how do I do dedupe logic upserts in Redshift? Say, for example, we have that table we've been working with, this deep dive table here, and I had a CSV file that I wanted to ingest. And this CSV file has data in it that's going to do an update to 2 of the rows here, and it's going to add 2 additional rows to that table. How do we do this? What we end up doing is we want to load that CSV file into a staging table. Then what we're going to do is we're going to delete the duplicate rows, or the rows that are going to match, out of the production table. And then we're going to insert every row from that staging table into our production table. The SQL for this, we're going to start with a transaction. Remember when I was talking about the global commits and they're a bit expensive still? We're going to wrap all of this workflow in a transaction. It's also kind of good because if something were to fail halfway through, it would either all happen or roll back. We're going to create a temporary table because temporary tables write twice as fast. I'm going to use this like keyword here, which is going to copy over the distribution style from our deep dive table. And it's also going to copy over compression settings from that deep dive table as well. Then I'm going to copy into that staging table that I created, that CSV file. Notice I kind of redundantly put in comp update off. That means I don't want Redshift to try to figure out the compression for this because it already has it from the deep dive table. Then what we're going to do is we're going to delete all of the rows in the deep dive table that match in that staging table. And I'm going to insert every row over into the deep dive table. I'm going to drop the staging table, and I'm going to commit the transaction, and all of this will happen, or it all will roll back. So this is the best way, the fastest way to do this type of logic. I've seen it done with update statements. It technically works, but this is faster. So our best practices, just a summary, wrap all the workflows in explicit transactions. Consider, if you can, using drop table, truncate instead of using delete statements if it makes sense. Use temporary tables. If you can, for your staging tables. If you do need a permanent table, we have a backup no option. Consider using that as well. So that disables the backup to S3 for that staging table. Make sure that if you do have these staging tables and prod tables, if they can share the same distribution key, that will make that insert into select much faster. Turn off automatic compression for these staging tables when you're loading data in, or apply compression manually, like with using the like statement. The reason why sometimes I'll see these workflows that are creating a staging table, and then Redshift figures out the compression for it, and then they drop the staging table, and then they create the staging table again. Redshift figures out the compression again, and that happens over and over again every 15 minutes. Very wasteful. So apply compression to those tables. Word about vacuum and analyze. I was talking about those ghost rows, or what happens when we tag rows as for deletion. We have a vacuum command in Redshift. Vacuum for deletes is automatic. It runs in the background for you automatically. We released that recently, so we have been working towards making vacuum fully automatic. Today it only does the deletes, so you do still need to do the secondary task or schedule that at some point, which is where we globally sort the table. We have Analyze, which also collects statistics. That is also now automatic as well. So we have released both vacuum, delete only, automatic, and Analyze. So those happen in the background now. Our best practices then would be run vacuum still at this moment until we get auto vacuum sort out. Most customers run it once a day, maybe on weekends. So that's really all you have to do, is maybe run it at the end of your ETL. Just do a global sort. So I'm going to jump into workload management here. Workload management is how we separate various workloads in Redshift. So if, say, you had 2 types of users, maybe your dashboard users, your data science and analyst users, and you wanted to kind of separate those workloads, throttle one versus the other, give priority to one type of workload. That's what WLM is meant for. So I'm going to go through some of the terminology about what makes up WLM. Queues, every SQL query that executes in Redshift will execute in one queue. So basically what will happen is, based on your user or based on a session variable, that will direct which queue that query will be executed in. We also have a concept that we call short query acceleration. It's just quite literally a checkbox in the console. And you can either disable it or leave it on. I recommend leaving it on. And what this feature does is, if a queue is full and we detect that the incoming query is a short running query, maybe it's only going to run in a few seconds, we bounce that into a special queue that we call the short query queue, and it runs immediately. So the idea here is to try to make short running queries continue to run even if the system is fully loaded up. The next concept that we have is query slots. The query slots are how we divide up each one of the queues. So we have a queue, and it's divided into slots. In the console, it's called concurrency. In Redshift, it's called slots. A little bit of confusion there sometimes. But they really kind of mean the exact same thing. Then I usually don't talk about upcoming preview features in a best practice talk because I try to keep with the features that are available. But this one's such a big feature, I really wanted to put it in here. We just released or announced what we call concurrency scaling. It was announced on Wednesday. Actually, it was announced last week, actually. So concurrency scaling it's an attribute of the queue, and you can enable it so that when the queue is full, basically what will happen is the queries in it will be routed to transient Redshift clusters. So we will manage that fully, and it is quite literally just a drop-down whether or not you want queries in that queue to route to secondary clusters. Fully managed for you. You don't do anything other than select that option, and basically that's it. So I'm going to come up with a use case. This is a very typical use case that I see with a lot of customers. Light ingestion kind of continually happening throughout the day, a little bit of just light loading. Then during the business hours, there's a lot of reporting going on, business users, that sort of thing. And then in the evening is when the typical large ingestion of data happens. Obviously, various users, business reports, analysts, DBAs, that sort of thing. So how I would recommend setting up WLM for such a scenario is I would create one queue here, which I'd call the ingestion queue. And I'd keep the concurrency or the slots on that quite low, probably 2. But I would give each slot quite a bit of memory as well. So in this case, there's 20% memory assigned. That means that each slot or concurrency, every query, is going to get about 10% memory. I am not going to enable, in this case, concurrency scaling for this queue. I figure it's a fairly predictable workload. I know when it's going to run, and I'm fairly confident that that will work. Then I have my dashboard queue, which is, we'll say, maybe Tableau or something like that. And I'm going to set the concurrency for this actually quite a bit higher, up to 10. However, each query, in this case, is only going to get 5% of the cluster memory when it executes. I'm also, in this case, just as an example, going to set a timeout of 2 minutes. I'm also going to enable concurrency scaling for this queue. So what that means is if there were a large number of queries that were running against this, maybe you hit 15 queries, what would happen is once you went over 10, the queries would begin to queue. With concurrency scaling enabled, we will in the background create these transient clusters and begin routing those queries to those clusters, clear the backlog, and then we can get rid of those transient clusters. Then at the end there, I have the default queue, which is kind of the, if you're not doing ingestion, you're not a dashboard, you end up running in here. I've just set the concurrency fairly low, 25% memory. And it would kind of be business requirements whether or not you wanted to enable concurrency scaling. I just kind of left it as either, just to make it as an example. One thing that some of you may have noticed is if you add up that memory, it only adds up to 95%. I did that on purpose. If you leave unassigned memory, it goes into a general pool, and it'll be used on a first-come, first-served basis by any queue, any query. So that's basically what would happen to that memory. And my best practices for this would be to enable short query acceleration. The next thing is we also have what we call a super user queue. I wouldn't say it's like a totally hidden queue. It's just it's not visible in the console. So a lot of people don't realize it's there. It is in the documentation. It is a queue that anyone who is a super user can change to, but you do have to manually set that variable, and you can use this special super user queue. It's typically used for DBA type operations. Maybe you want to find out who's running what query and maybe cancel a query, something like that. This next piece here, QMR, it's really an extension to WLM. We built it primarily for those of you who have users that connect to your cluster that you wish didn't connect to your cluster. It really is meant for runaway queries. So you can programmatically set up a set of rules to detect, say, like a Cartesian product, or to detect if someone decides it's a good idea to return 100 million records. And so you can have Redshift kill that query rather than it consuming a ton of resources, you getting paged or whatever and having to log in and find out who's doing what and kill someone's query. So it was really meant to programmatically take care of that. The other use case that we found very useful, it wasn't what this was primarily built for, was logging queries. When we built it, we didn't want just to obviously abort. Maybe in certain cases, you might just want to log. One best practice that I give for a lot of customers that are setting up QMR is just set up rules to log these long-running queries or these expensive queries, even if you don't want to just programmatically kill them. And that way you can go back through and look at the SQL on what's running and maybe adjust things. Just some examples of what you can kind of do with QMR and how it's kind of structured and how it's like this if-then, and you pick these various metrics. Like I said, one of my favorite ones is the return row count. The reason I bring that one up is typically if you're returning a large number of rows, it actually is better to just use the unload command and unload it to S3 into, say, CSV format or something like that. It's significantly faster than dragging the data through the leader node. So just general best practices on WLM and QMR. I always say keep the number of queues to a minimum. Sometimes I'll get on site with a customer and they'll have like 6 queues defined. And then this SQL query or this script I have on GitHub here, this is a script that you can execute on an existing cluster, and it'll look at like the last 3 days of what's happened, and it'll tell you the peak number or queue depth on every one of your queues. What I usually see is customers that define like 6 queues, they have like 3 of them that are unused, and they have all these resources assigned to them. So usually I always say keep things to a minimum on the number of WLM queues. 3 or 4 is probably a good limit. Use WLM to ingest your ELT, especially during the day. I usually say during the day, maybe keep it to like 2, maybe 3, or else it will have an impact on your queries, your reports and such. The global number of concurrency or number of slots in the clusters, we usually recommend about 15. That's about that's a sweet spot where you're going to get peak performance. That's why we would give that recommendation. You technically can tune it all the way up to 50. However, if you tune it all the way up to 50, that means the most any slot could have would be 2% memory, basically. So if you just went, I'm just going to have 50 slots, every query would get 2%, and you might end up with a whole bunch of queries that start spilling a disk. So keep that to about 15 or less. I usually find it's somewhere between 12 and 18 is the sweet spot for most customers. It's about 15 is bang on. Last thing I mentioned, log your long-running queries with QMR and save that super user queue for admin tasks. So cluster sizing, one of the most frequently asked things I get when customers especially are starting a POC. We have 2 different flavors of nodes in Redshift. One is our DC2, which is our dense compute, we call it, which is SSD backed, and our dense storage node type, or DS2. That's magnetic disk backed, or just HDD. Then each of these node types come in 2 different sizes. We have a smaller size and an 8XL size, basically. You can see, one thing I'm going to just call out, you can see the slices there, 2 or 16, depending on the small instance type or the large one. So the first thing I'll always have a customer do is calculate the amount of uncompressed data that they believe they're going to have in their Redshift cluster. This just needs to be a ballpark estimate. Then what I say is we're going to assume that we're going to get 3 times compression ratio on this data. That's a very conservative number. Chances are there's a really good chance, in fact, it'll be closer to 4 times. And then we want to usually target somewhere, I think the sweet spot is around 30 to 40% free space. Ideally, I'd say you should be using at least 15% of the cluster. That'd probably be like you should at least use that. And I would say no more than 80%. So that's kind of the range where you want to be, but I think the sweet spot's between 30 and 40, and that's what I try and target. Then based on your performance requirements, you're going to either pick the magnetic disks or the SSDs. So if you're like, I really need high performance, pick SSDs, magnetic disks. And we always size Redshift by the amount of data that you have and pick the appropriate platform. So just as an example, say I have 20 terabytes of uncompressed data. What's going to end up happening is we'll just assume that's going to be about 6.7 terabytes after factoring in compression. Then depending on your performance requirements, we're either going to pick 4 of those DC2 8XLs or 5 of our DS2 extra large nodes. Both of those give approximately 10 terabytes of capacity, land us in that estimated sweet spot. If you end up getting better compression than you thought, you can resize. If the magnetic disks you started with weren't giving you the performance you needed, you can also resize into the other node type. And I'll talk about that right now. So we have 2 types of resizes in Redshift. We recently released what we call elastic resize. So if some of you haven't heard of that, that is actually quite new. The classic resize, which was the resize, our old resize, basically what it does is it transfers data from your original cluster into a new one that we provision. And that's why we can change the node type. One other interesting thing you can do with it is you can also enable or disable encryption on your Redshift cluster using that resize. The new elastic resize, what it does is we add and remove nodes from an existing cluster. So we're not doing the whole data transfer thing. I'll illustrate both of these. So let's just say we have a 3-node cluster here. These little white lines, there's 16 of those. I counted exactly. So you have 16 little slices there on this DC2 8XL node type. And let's say we wanted to resize this up to 4 nodes. What we would do, or what the service is going to do, is it's going to provision in the background a whole new cluster with the 4 nodes. We're going to drop your source cluster into read-only mode. Then we're going to do a binary transfer of all of this data, and we're going to redistribute it all across these slices. Once this operation is complete, we're then going to repoint the DNS, and we're going to bounce the connections to the original cluster. When everyone reconnects, they're reconnected to this new cluster. And that's how resize worked up until a few weeks ago. And still does work if you select classic resize. So now I'm going to talk about elastic resize. So I'm going to go with the same example. So I have the 3-node cluster here, each node with 16 slices. And when I select classic resize to go up to, or elastic resize to go up to 4 nodes, what we're going to do is we're going to immediately provision this new node. We're going to attach it to your cluster. We're also going to begin backing up all the data in the cluster. It's just an incremental backup. It's actually really fast. This operation takes roughly about 15-ish minutes. I know I have a bit of a time range on there. There is some certain cases where it does take longer, especially if you're ingesting data and such while this is happening. So when this part ends, what I'm going to do is I'm going to redistribute some of these slices. So if you see how there's those 16 little white lines, some of them just moved over. So what we do is we redistribute some of those slices from those 3 nodes to that 4th node. In this example, now every one of the nodes has 12 slices. So that's essentially how we do the resize. This operation to shuffle these slices around takes about 4 minutes. During this time, all of the connections, all of the in-flight queries are parked and held. We will resubmit them once this is done. With the exception of some writes that occur in a transaction. Unfortunately, those ones will be rolled back. Once that operation of shuffling is done, we then begin to stream the data out of S3 back into this new compute node that's been added to your cluster, and the cluster is fully readable and writable during this time. If you have in-flight queries, we'll just fetch that data immediately off S3 to fulfill that query. So with elastic resize, we have depending on your instance type that you start with and your original configuration, there are limits and ranges to where you can grow. So for example, I'm going to go through an example here with 4 nodes. So if we started with 4 nodes as our original configuration, and we were on the smaller instance types because they have so few slices, the only valid configurations to go on this one would be from 4 down to 2. You could go back up to 4 if you wanted, or all the way up to 8. So those are the valid configurations for that. If, however, you're on the 8XL node types, you have a lot more choice. So in this case, I have started with 4. I can either incrementally go up all the way up to 8. I can pick, or I could just jump all the way up to 8 if I wanted to, or I could go all the way down to 2 or 3. And you can pick and move anywhere within that based on what your cluster's original slice count was. So when would you use these? Well, one of the cases, this wasn't primarily what it was meant for, but one that we had a lot of customers using it for when we had this in beta was using it for when they knew they had a spiky workload. So we had customers using it especially for a nightly batch ingestion to speed that up. So for example, they would kick off an elastic resize, double like the size of their cluster, for example, so they get significantly more compute, do their ingestion, and then elastically resize back down once that was completed. You can use it to incrementally add storage, especially on the 8XLs, so it's really useful for that. So if you say, for example, in the example I had with 3 nodes needed extra storage and you want to go up to 4 nodes, I would recommend using elastic resize if that's an option. You'll use classic resize when you move between SSDs, HDDs, or if you wanted to change between a small node type and a larger node type. The biggest difference between them is the amount of time. So with the elastic resize, you get 4-ish minutes of parked connections. With the classic resize, it's somewhere between, usually I say it's an overnight operation. It can range depending on how much data we have to move, anywhere between 1 and 24 hours. We always try and have these completed within 24 hours. So best practices on cluster sizing. I always recommend 2 nodes. We have an option to run what we call single node clusters in Redshift. Single node clusters are really meant for dev, test, QA, just some experimentation, that sort of thing. I always recommend using a multi-node cluster in production so you get that redundancy, the safety of the second copy. Always maintain at least 20% free space in your Redshift cluster if you can. You can usually, maybe you might be able to get away with a little bit more than that, but what will end up happening is if there are temporary tables that are needed, intermediate tables, that sort of thing, those consume disk space. So for a lot of cases, it just simply makes sense to add an extra node, add some capacity so you don't get out of disk errors. If you happen to be one of these people who are still on a DC1, I know there are some Redshift users in here. If you're using DC1 instance types, please upgrade to DC2 instance types. You can resize from DC1 to DC2. It was about a year ago that we launched this new instance type, and it is significantly faster. In a lot of cases, they can be twice as fast. We have made it very easy to upgrade. You can just do the resize. If you have reserved instances on DC1, we are letting you migrate your reserved instance at no cost to a DC2 reserved instance. So you can just move the reserved instance, and you can do that now in the console. We want you to be using the latest hardware with Redshift wherever possible. We want you to have the best experience with Redshift, so we don't ever want you lingering around on old hardware. Some additional resources. I had these GitHub links littered throughout the presentation. We have what we call Amazon Redshift utilities on GitHub. This is a collection of scripts and views and that sort of thing that we internally have built when we work with customers, and we've exposed that and put that out there. So there are a lot of these things that we find very useful for diagnosing and debugging things. I particularly love the admin scripts and admin views. A couple of blogs that are very useful. The Design Playbook is a very in-depth blog. It goes through a ton of different concepts. It talks about some of the more advanced things. The top 10 tuning techniques, a lot of it I've covered in here, but there are a couple of things I'm not able to fit into a 1-hour session that are on there as well. And then we have, if you're using Amazon Redshift Spectrum, a handful of best practices for that as well. Thank you guys very much. I hope you guys enjoyed this and reInvent.